Welcome to LT Lyons Township High School AP Physics. Today we got an example involving simple harmonic motion. In particular, I got a cart attached with two springs. It's a little hard to see in the video probably. That one's blue, that one's gold, LT colors. And this guy is going to bob back and forth between two endpoints. So that's your simple harmonic motion. Now, there's some data I'm going to give you about that, and there's some things we're going to determine. So the cart is going to oscillate with an amplitude A, okay? We're going to make A 10 centimeters. The period, that wouldn't normally be a given. I actually timed this. So spend a moment. I actually timed 10 cycles divided by 10, and I got that. I did it a couple times, and I got about that for my average time for one cycle. The mass of the cart and the blocks on it is 1.5 kilograms. From that, we're going to determine the spring constant. We're going to determine the total energy of the system. We're going to determine both the max velocity and the velocity when it's 4 centimeters from equilibrium, so like, not quite halfway. And then the max acceleration and the max, or the acceleration at the 4 centimeter mark as well, okay? All right, so if you need to, you can copy that down. So here we go. So how am I going to find the spring constant K? Because I need that to solve this problem. Well, if you were in Physics C, we actually learn how to find each spring constant, or any of you guys can find the spring constant. It's force over displacement. You could hang them up, add some weight, measure the displacement, and you get spring constants. And then you have to figure out from those two spring constants what the total spring constant is, and it's not the sum of these two, by the way. So there's a process for that. For Physics 1, that's not something you have to do. But we have to still figure out the spring constant, but we're going to use the period to do that. We know that the period of a mass bobbing around the spring is 2 pi root m over k. So we know that, and we got the period, we got the mass, we can find k. Now if you solve this for k, so you divide both sides by 2 pi, you square everything, you flip it over, and you move the mass, which will be down here, you move it up there, you would get 4 pi squared m over t squared. Let's see, did I do my algebra right? Yes. All right. And we got all those numbers, right? 4, you got pi squared, the mass was 1.5, and then the period was 0.962, and we got to square that. So we got our spring constant right off the bat. And for a spring constant, when I got this, I got about 64 newtons per meter. So about 64.0, but I guarantee you this ain't as that accurate to the nearest 3 digits anyway, so we'll call it this 64. So that's our spring constant, 64 newtons per meter. Okay, that's the effective spring constant of these two springs. All right, so now if I displace this 10 centimeters and let it go, okay, how much total energy does my system have? Okay, well, you can pick any point you want. So I can either pick an end, I can pick when it's going through the center at equilibrium, I can pick somewhere in between. I will choose the end. So at the end, when this thing's bobbing back and forth, when it gets to here, it stopped moving. So the only kind of energy it has at that moment is spring potential energy. So depending on your teacher or your textbook or whatever, we use U elastic, potential energy elastic. So what is that? What's the equation for that? Well, it's 1/2 kx squared. And since we're at the end of the motion, we can rewrite this as 1/2 k a squared. And because the cart at that moment momentarily comes to rest, there is no kinetic energy, so this just is all of our energy. And if you plug and chug the numbers, you got 1/2 times 64 times the amplitude is 10 centimeters, which is 0.1 meters, so 0.1 squared. So you get 32 times 0.01, you get 0.32 joules of energy, okay? Now, by the way, a quick note on that ain't much, okay? It's a small cart, not moving very fast and not displaced very much, so there's not a whole lot of total energy of our system. All right, the next question was what's Vmax, okay? For that, we're going to use conservation of energy. I will derive a shortcut formula for you, but you should start with conservation of energy and just go from there. So we're going to go from, when you use conservation of energy, you always pick 2 points. You look at an object as it moves from point A to point B. The 2 points that I'm going to use will be the end, okay, and then equilibrium, okay? So like when the cart's over here, that'll be point A, okay, and that's a little confusing. That's not the amplitude. And then when it's in the center, we'll call that point B, okay? So at point A, the only kind of energy the cart has is spring potential energy, and we know that number, it's 0.32 joules. When it's going through equilibrium, at that point, the only kind of energy it's got is kinetic energy. So all this potential energy turns into kinetic energy. So I'll do that up here. So now what I'm going to do, though, is I'm going to derive an equation for that, and then we'll solve, okay? So we're going to set potential energy at point A equal to kinetic energy at point B, okay? At point A, this is 1/2 kx squared. At point B, it's 1/2 mv squared, okay? Now the halves drop out. I'm trying to solve for v. V is square root of kx squared over m. Now if you're looking at v max, you get root k a squared over m. Now I will make a note, okay? You can pull the a out and it becomes an a, and you get root k over m. Root k over m is called the angular frequency of the system. It's omega. So in a textbook, you might see this, a omega. I prefer not to do it that way. I prefer to actually work this out, and you can get to that point, that's okay, but I don't like to write that because then it gets a little confusing on what that is. Okay, so anyway, but I do know all of these, so we can plug them in. So V max is A, which is 0.1. Okay, oh, and before we do this, how does this thing go from 10 centimeters? What does it look like its max velocity is? Okay, so I start from here, get to here. Okay, well, it sure ain't going very fast, right? Maybe a mile or two an hour at most, all right? So we know we're going to get a pretty small number when we get an answer here. So it's 0.1 root k, which we got as 64 over the mass, which is 1.5, okay? When I plug and chug those numbers in, okay, I got 0.65, okay? So I got 0.65 meters per second, which would be a little over 1 mile an hour, give or take. So yes, not going very fast, okay? But that's kind of what we expected. There's a little cart moving around on the track, okay? Now, the other things we asked were, what is the velocity at the 4 centimeter mark? So we're going to start with our conservation of energy again, okay? But this time, when we start here, I'll start at the end point again. I only have spring potential energy. When I'm at the 4 centimeter mark, okay, I have the spring's still stretched out, so I still have some spring potential energy, and I have kinetic energy. I'm moving. So this will be my point A, the far end. Point B will be the 4 centimeter mark from equilibrium. So it's the same process, except for this side's the same, and I'll just write that as 1/2 k a squared, right? On the right-hand side, when we are 4 centimeters away from equilibrium, that's here, okay, the cart is moving and the springs are still stretched out. So we've got kinetic energy, 1/2 mv squared, plus you got some potential, 1/2 k x squared. Now remember, A is 10 centimeters, x is 4 centimeters. Again, we're going to solve for v. The halves all drop out. And if you solve for v, you get the square root of ka squared minus kx squared. I can factor the k out. You get a squared minus x squared all over the mass, okay? Now again, the root k over m, that's your angular frequency of your system. If you're in physics C, you talk all about that, but I'm going to leave that in there like that. All right, so in this case, the v at the 4 centimeter mark is root k, which we got a 64 for. A is 10 centimeters, otherwise known as 0.1 meter, got to square that, minus x, which is 4 centimeters, which is 0.04 meters, so 0.04 squared, all over the mass of your system, which is 1.5. And I get the velocity at the 4 centimeter mark to be, I got 0.60. 0.60 meters per second. Now notice that it's not too far off of the max speed of 0.65. That's because we're pretty close to the equilibrium position, and the kart's not accelerating very much anymore at that point. It's kind of almost done accelerating. So you've almost reached your max velocity at that point. All right, finally, the last two questions involve acceleration. The max acceleration and then the acceleration at 4 centimeter mark. Where's the max acceleration going to occur? Okay. Well, right now, the acceleration is 0. So when you're going through the middle, when the kart is going through equilibrium, at this point here, it's at its max velocity, which means you're done accelerating, which means your acceleration is 0. So at equilibrium, your acceleration is 0. On the other hand, when you're at stretched to one end, that's where you have the most acceleration, where the kart tries to change its velocity as rapidly as possible. The springs are tugging the most when the kart is at either end point. So your max acceleration occurs at either end point, at the amplitude of your motion. So either here or there. That's where your max acceleration occurs. Now to calculate that, that's actually very easy. We're going to use net force equals ma. All right, well, what's your force? What's the force created by a spring? Well, that's kx equals ma. So that's the force of a spring, kx. And you solve for a. Now, a max will be k times the amplitude of your motion. That's your 10 centimeters over the mass. So for us, that's 64 times 0.1 over the mass. And for me, when I plugged and chugged those into the calculator, I got, what did I get? 4.3. So I got 4.3 meters per second per second. So that's my maximum acceleration. To find the acceleration when you're at the 4 centimeter mark, instead of putting a 0.1 here, you just put a 0.04 there. Okay? So in that case, your acceleration at the 4 centimeter mark will be 64 times 0.04 over 1.5, which will simply be 40% of that, okay, 0.04 over 1. And when I did that, I got 1.7 meters per second, okay? So that's a linear function. So that's an example of an oscillator, a simple harmonic motion, using energy to find velocities and such. I will make one note. If I were to take this and turn it vertical, okay, all this stuff would be the same. The only thing you got to be real careful of is if you do that, you've got to measure from equilibrium, from where that kart wants to be at rest. So if this whole thing is vertical, or I got the kart hanging from a spring, you hang the kart from the spring, let it stop. You measure everything from there. You measure your displacements from there, your velocities from there, your position from there, and everything will be the same. If you were to hang the kart from a spring and then pick somewhere else besides that equilibrium point to measure from, well, then when you talk about energy, then you'd have to worry about gravitational potential energy, MGH. But in this case, you don't have to worry about it because if you pick the equilibrium point as your 0 point, it turns out that MGH is not a factor. And there's a lot of math involved with that. But anyway, I hope that problem was helpful, and thank you very much.